Alright, so this is the last section, 7.6, which is our multiple eigenvalue solutions. So let's start with a small example. So let's suppose A is a 2 by 2 matrix. And it only has one eigenvalue, lambda. Because it's a 2 by 2 matrix, it only has one eigenvalue, that means this lambda has multiplicity 2. Okay. So let's discuss two cases. The first case we have learned before, which is the case where A is diagonalizable, which means there are two eigenvectors, associated eigenvectors, v1 and v2. And v1 and v2 being eigenvectors means that A times v1 equals to lambda times v1, and A times v2 equals to lambda times v2. Notice that these are equivalent to A minus lambda I times v1 equal to 0, and A minus lambda I equals to times v2 equal to 0. Okay. So we're going to take these conditions and draw it, rewrite it as a diagram, because we're going to be using this diagram in the other case. So we're going to write v1 and an arrow means multiplying by A minus lambda I. So when we multiply A minus lambda I to v1, we get 0. And same thing, same thing for v2. Yep. So an arrow means multiplying by A minus lambda I. So in this case, there's an arrow going from v1 to 0, and then there's another arrow going from v2 to 0. Okay. So in this case, A is diagonalizable, and A is equal to P inverse, where P is the matrix with column vectors v1 and v2, and D is the diagonal matrix with diagonals being lambda. Okay, so in this case, because lambda has multiplicity 2, and it has two associated eigenvectors, so in this case we say lambda is complete, because the multiplicity equals to the number of eigenvectors. Okay, so that's the case we know before. Now let's deal with the other case, which is the case where A is not diagonalizable. So because lambda has multiplicity 2, if we only have one associated eigenvector, it's called v1, then it's not diagonalizable because A is a 2 by 2 matrix. We need two eigenvectors to diagonalize A. So that's not good, but let's still write down what happens with v1. So v1 is still an eigenvector, so A times v1 is equal to lambda times v1, which the same implies that A minus lambda I times v1 equal to 0. So we can still take this and draw the diagram. The diagram says that v1 multiplying by A minus lambda I gives you 0. But we don't have v2 because there's only one eigenvector. And in this case, what we do is we chain it this way. So in this case, we solve A minus lambda I times v2 equal to v1. So this is equivalent to AV2 equals to v1 plus lambda v2. Okay, so v2 is technically not an eigenvector. v2 is called a generalized eigenvector. This is the best alternative we get in this case. So v2, when you multiply by A minus lambda I, gives you v1. So this is called a chain of generalized eigenvector. Okay. So in this case, A technically is not diagonalizable, but if you take these conditions and you rewrite it, you will realize that A is equal to P times J times P inverse. P is still the same matrix. the columns are v1 and v2, and J is almost a diagonal matrix, so lambda on the diagonal, but there's a 1 up here. This is called the Jordan normal form. That's why it's called J. Okay. So in this case, because lambda has multiplicity 2, and there's only one associated vector, we say lambda is defective. And to specify how defective it is, we take the difference of the multiplicity and associated vector. So the defect, D, is equal to the multiplicity, which is 2, minus the number of associated eigenvectors. Which is equal to 1. Okay, so not every matrix is diagonalizable, but every matrix has a Jordan normal form. Okay, so this is a 2x2 example. Let's extend this. So now, suppose we have a diffee Q, still 2x2 by the way. Suppose we have differential equation x prime equals to a times x. We just learned a is equal to p times j times p inverse. So x prime is equal to pj p inverse times x. And the common trick is multiply by p inverse on both sides on the left to cancel these two. So we get p inverse x prime equals to j p inverse x. And you let y equals to p times inverse times x. Then this is y prime, and this is y. So we get, let me move to the left because we need space, y prime equals to j times y. This means y1, y2 equals to lambda 1, 0 lambda times y1, y2 prime on the left hand side. So if we simplify this, we get two equations. The second one is the easier one. The second one tells you y2 prime is lambda y2, which we know how to solve. The first one tells you that y1 prime equals to lambda y1 plus y2. Okay, so there are two differential equations. Again, we know how to solve the second one easily. The second one tells you that y2 is c2 times e to the lambda t. Alright, but the first one, this is not homogeneous. So because it's not homogeneous, we need to solve for a complementary solution and particular solution. So for the complementary solution, it's the easier part. We solve the homogeneous part, which is y1 prime equal to lambda y1. So we get the complementary solution is c1 times e to the lambda t. And the particular solution, so because the y2 has e to the lambda t, which appears in the complementary solution, so for the particular solution, we have to multiply by t. So the guess is k times t, kt e to the lambda t. And if you plug it in and solve for k, we get k equal to c2. So y1, the solution is yc plus yp. So it's c1 e to the lambda t plus c2 t e to the lambda t. So that's y1 and y2. And because y is p inverse times x, this tells you that x is py. This is equal to v1, v2 times y1, y2. So this is equal to y1, v1 plus y2, v2. y1 is c1 e to the lambda t plus c2 t e to the lambda t times v1 plus y2 is C2 e to the lambda t times V2. So for convenience, we want to separate C1 and C2. So these two terms have, only this term has C1. So this is C1 e to the lambda t times V1, and these two terms have C2. So plus C2 e to the lambda t times TV1 plus V2. Yep. So this is how we solve differential equations when you have a 2x2 matrix which is not diagonalizable. So we'll do an example in the next video.